Right, we are going to do section 6.2, enthalpy and calorimetry. Some of you might see the word calorimetry and think, oh no, I don't like this topic, but it's going to be so much easier the second time around. So, first thing we have to relearn is calorimetry. We have a very simple equation. If you remember it, try to think of it. I'm going to show it to you in a moment. And here it is. Q is ms delta T. Try to remember what those different variables stand for. The Q, heat flow. M, mass. S, specific heat capacity. And delta T is the change in temperature. So you might want to pause the video for a moment here while you write all of this down. I will go over it, but again, you might want to pause to get that all written down, and then I'm going to talk about it. You don't need to pause if you don't want to. All right, so this Q is the heat flow. It's how much heat flows into or out of a calorimeter. M, it's the mass of everything in the calorimeter. So if you have a calorimeter that contains water and some chemicals in it, it's the total mass of that water and all the chemicals in the water. S is the specific heat capacity of the calorimeter contents. Now, usually, we use the value of 1 calorie per gram degree Celsius, or 4.18 joules per gram degree Celsius. No, 1 calorie is 4.18 joules. And that is the heat capacity, the specific heat capacity for water. When we have a solution in our calorimeters, we usually assume that that solution has the same specific heat capacity as pure water. Last variable in here is delta T, the change in temperature. Right here, T final minus T initial. Hopefully this is bringing back some good memories. Now, for a reaction occurring in a calorimeter, we have another equation. And that equation is Q of the calorimeter is negative delta H for the amount of chemical reacted. Sometimes we write this as Q reaction. Notice we don't write delta H reaction because it's not the heat of reaction. It's for the amount of chemical that has reacted, which is not necessarily the heat of reaction. This delta H here is not necessarily, excuse me, the heat of reaction. This whole thing is for the amount of chemical reacted. So it's the amount of heat produced or used for the amount of chemical that's reacted. I know I've repeated that 3 or 4 times now. It's to get that, make sure that it's in your head that this delta H here is only for the amount of chemical reacted, not delta H reaction. We end up using that quantity to find the heat of reaction typically. All right. Don't ever forget this negative sign right here. That's one of the most common errors. This delta H that I've written there is the same thing as the Q reaction. You can choose to write it either way, Q reaction or delta H. But the important piece is Q of the calorimeter is always equal and opposite to delta H for the amount reacted or Q of the reaction. So let's do a problem. There's a big problem written here. You might want to pause and get that all written down. So it's up to you if you want to pause at this point to write this entire problem down. It'll take a little while. I'm going to go into how to solve this. Okay. Got a lot of information here. So, sorry about that. Let's see what we have. First, we're going to separate the calorimeter from the reaction. And note, I'm using this Q reaction and Q cal. I like using Qs because the Q tells me that I'm not talking about delta H reaction. I'm talking about the heat flow for this particular amount reacting. So Q calorimeter, what do I know? I know that I have 100 milliliters of HCl solution. And hopefully you remember that the density of a water solution is density of water is approximately 1 gram per milliliter. For all of these calorimetry problems, we're always going to assume that the solution has the same density as pure water. And that's not always true, but that's the assumption we will always use for this class and for the AP Chem test. If there is a different density, they will give it to you. So we know that that is 100 grams, because it's 1 gram per mil. What else is in this calorimeter? We have also 100 mils of the NaOH solution. So we'll write down 100 mils of the NaOH solution. And that's another 100 grams. What else do I know about the calorimeter? Let's see. It's a water solution, so I know the heat capacity. SC. The specific heat, S. Some books use C, some use S. The specific heat capacity is going to be 4.18 joules per gram degree Celsius. It would be okay if you used 1 calorie per gram degree Celsius. When we calculate the heat change, since they did not state whether we wanted this in joules or calories, you could use either one. I'm going to use the joule value. Okay, I also know my initial and final temperature. Initially, we're at 22.5 degrees Celsius, and at the end we're at 25.86. So, T initial is 22.5 degrees Celsius. T final is, what was it? Let's see, 25.86 degrees Celsius. So I have all the information I need about my calorimeter. I've got my total mass right here. I'm going to add those together. I've got my S, and I've got T final minus T initial. For my Q reaction, well, I've got a reaction here. Let's see, what do I know about my reaction? Okay. I know, let me move this down a little bit. Okay, I know that I have, for NaOH, let's see, it's right here. I've got 100 milliliters of 0.5 molar. And how many moles is that going to be? 0.5 moles per liter times 0.1 liters, 0.05 moles. And my HCl, I've also got 100 milliliters. And I have 0.5 molar again. And my 100 mils is 0.1 liters and 0.5 moles per liter. This will also equal 0.05 moles. Now let's note here, I'm not going to have a limiting reactant, am I? I have exactly the right amounts of each reactant. They balance each other out because we have a 1-to-1 ratio of the coefficients, and we have a 1-to-1 ratio of what's present for each reactant. So for Q reaction, I've got 0.05 moles HCl, 0.05 moles of NaOH. Okay, let's do some calculations now. I have my equation, QCal is negative Q reaction. So I can solve for my Q reaction. Q reaction is going to be negative QCal. And now I just plug everything in for MS delta T. My mass will be 200 grams, 3 sig figs there. S, 4.18 joules per gram degree Celsius. And in this situation, I do not have to convert to Kelvin because, since I'm taking a difference in temperatures, final minus initial, the kelvins would just cancel out. So 25.86 degrees Celsius minus 22.50 degrees Celsius. I'm running out of room there. And now I just check my units and plug this into the calculator. Grams cancel. The Celsius will cancel. I will end up with joules. And what do we get? Okay, so hopefully you're getting negative 2810 joules, give or take a little bit. Sig figs. We should keep 3 sig figs here. When we have our temperature, when we do this subtraction, we will end up keeping only 3 sig figs because we would keep everything to the hundredths place. And we have 3 sig figs right here, and this is 3 sig figs right here. So we're going to keep our answer 2810 joules, negative 2810 joules. The negative comes from this negative sign right here. I forgot to write that here. All right. So I know that negative 2810 joules is produced from 0.05 moles. So let's look at this. The way we solve this now is I know it's negative 2810 joules per 0.05 moles of HCl. And I now look at my reaction for my reaction coefficient. The coefficient for HCl is 1. If it had been a 2, I would do something slightly different, and I'll show you what I would do. So I have negative 2810 joules per 0.05 moles times 1 mole per reaction. And that gives me, let's see, negative 56,200 joules per reaction. And I look at my question to make sure I'm reporting this correctly. The question said, find the heat change, delta H, on a molar basis. So the reaction was for 1 mole. So I'm giving the final answer per reaction, which is also per mole because the reaction was 1 mole. Now if the reaction happened to have 2 moles and I said I want the enthalpy change for the reaction and there was a 2 in there, I would have changed that number right there to whatever coefficient I had for the chemical of interest. You might be wondering, why didn't I add together the moles of HCl and the moles of NaOH? If you're not wondering that, you can fast forward through this part of the discussion. But let's look back up here. Note I had 0.05 moles of 2 different chemicals. And in this chemical reaction, I need both of those chemicals to react in order to make some products. So I do not add together the 2 chemicals. I don't add the 0.05 moles to one another because I need each of them. I need 1 mole of NaOH and a mole of HCl. So I need both this and this to make the reaction occur. That's why I don't add the moles together. And that's why right here, oh dear, that's why right here I only have my 0.05 moles of HCl. I could have substituted 0.05 moles of NaOH in the bottom here, and I would have gotten the same result. If I had done that, I would have NaOH right there, and again, I would have gotten the same result. So let's do some more problems. That was not enough. I know you're going to need a little more practice here. All right, here's a new problem, and again, you might want to pause while you write down the whole question. La-di-da-da-da-da-da. Okay, if you haven't paused by now, just hopefully you've got this all written down because I'm going to start going through the solution. So we're going to separate this out into the calorimeter and the reaction. Okay. Calorimeter, what do we know? We know that in the calorimeter we have 3.53 grams of NH4NO3, and we also have 80.0 milliliters of water. You have to remember that water has a density of 1 gram per mil, so that's going to be 80 grams of water. And let's just make a note. So the total mass is going to be 83, oops, sorry about that, 83.53 grams, but really I can only keep that up to the tenths place because when we're looking at sig figs here, we look at precision when we are adding numbers, and the first number is only to the the first numbers to the hundredths, second numbers to the tenths, so I can only keep my answer to the tenths place. Okay, I know M. S. Okay, we have a coffee cup calorimeter, so S is going to be 4.18. To one more sig fig, it's actually 4.184, but we're not going to worry about that right now. Joules per gram degrees Celsius. And we also have our temperatures right here. So, oh, the temperature went down. T initial is 21.6 degrees Celsius. T final is going to be 18.1 degrees Celsius. Let's just think about this for a minute. Let's think about, should our final answer be positive or negative? We put this ammonium nitrate into water. The temperature of the water goes down. So does the water get cold or hotter? Hopefully you realize the water got colder. Now if the water's getting colder, is the water taking in or giving off heat? Hopefully you got it. The water is giving off heat. Well, if the water is giving off heat and the reaction is equal and opposite to what happens to the water, and now remember the water was giving off heat, so the reaction is taking in heat. Hopefully I said that right the first time. The water is giving off its heat. That's why its temperature goes down. The reaction is taking in heat. Its enthalpy is actually increasing. So should that be endo or exothermic if the reaction's taking in heat? Hopefully you realize it's going to be endothermic. And let's see if our answer at the end ends up making sense. We always want to check, do things make sense? So we're going to go over to Q reaction right now. We've got everything we need for the calorimeter. For the reaction, oh dear, my students are walking in really. So for the reaction, here's our reaction, and we want the information on reactants. Well, the only information I have about the reactants is right here, 3.53 grams of ammonium nitrate react. That's all I have. So I have enough information to start calculating my Q calorimeter, MS delta T. So let's start plugging everything in. We have 83.5 grams. Heat capacity, specific heat capacity, 4.18 joules per gram degrees Celsius. And our delta T final minus initial degrees Celsius. So let's check our units. Grams cancel, degrees Celsius cancels, and now we need to calculate that out. Okay, so what we find here is that we get negative 1221.6, but now sig figs get a bit complicated here. Because right here, when we do the subtraction, we can only keep our answer to the tenths place. So let's see, 5, negative 3.5. And right there, I only get to keep 2 sig figs, so my answer can actually only have 2 sig figs in it. So negative 1200 joules. That's my Q calorimeter. Now, we know Q reaction is negative Q cal, so that's going to be positive 1200 joules. All right, positive endothermic. We're good. Remember we had that little conversation earlier when I was the only one speaking? Wasn't actually a conversation, but I went through the whole process of should this be endo or exo. We decided, hopefully we all decided, this should be endothermic, and the positive Q reaction tells us this is an endothermic reaction. Now, we know it's 1200 joules for, let's see, 3.53 grams. 1,200 joules per 3.53 grams of NH4NO3. And I need to find delta H for an entire reaction. Our reaction has 2 moles in it. So first I'm going to have to convert my grams to moles, so I have to figure out my molar mass of the NH4NO3. Let's see, 14, 28, 28, and 48. I'm going to pause this and calculate. Okay, it comes out to 80.06. Now I did not need to keep that many sig figs for my molar mass. And why I wrote grams per mole, I'm not quite sure. Just grams per mole. And now we have to look at the reaction coefficient. I have 2 moles of ammonium nitrate, and this is NH4NO3. It's my ammonium nitrate. I have 2 moles of ammonium nitrate. Why am I putting this in the numerator and not the denominator? Hopefully you're looking at your units and you're seeing this. My grams cancel here. And now I have to cancel my moles out, which is why I put the moles in the numerator. And it's 2 moles of NH4NO3 per 1 reaction. 2 moles per reaction. So now I calculate this out and I get, all right, and we get 54 kilojoules. Now I actually had 54,390 joules. But I didn't want to write all those zeros, so I just converted it to kilojoules. And I could only keep 2 sig figs because, whoa, not because of that. Because of this number right here, I could only keep 2 sig figs. So my final answer has 2 sig figs. All right, now you're going to try number 54 from chapter 6. And if you've already spent an hour and a half on homework on this class, just stop right there. If you haven't, go ahead and try 53. And there's a note here. You might want to make sure you have this either written down or that you are looking at it on the web because it's important. It's a little bit different. So I've given you how it's different here. Okay, I'm going to pause this. I'm going to stop this actually, so you should pause if you need to write anything down.